Right, so in this lesson we're going to look at Newton's second law of motion. And Newton's second law of motion is based off that idea of making things move. Now, the definition of Newton's second law of motion is when a net force acts on an object, the object will accelerate in the direction of the force at an acceleration directly proportional to the force and inversely proportional to the mass of the object. And it is dictated by this equation here. If net is equal to the mass times the acceleration. So if we break down the definition according to the CAPS document, it is saying that a net force is the resultant force. It's the forces, all forces acting upon that object, which gives us a single net or resultant force. Now, when all of those forces are acting on that object, we end up getting a specific one force. So let's just pretend that if we have a free force diagram or free body diagram, then if we have a force going in the y direction and a force going in the x direction, the net force which would be created would be a combination of both forces given. Okay, now then we go on to the next part saying there's directly proportional to the force is acceleration, and inversely proportional is the mass. So essentially what you're saying is that the acceleration is directly proportional to force, but acceleration is directly proportional to the inverse of the mass. Now, this is basically saying that we increase force, we increase acceleration. But if we increase mass, we actually decrease acceleration. Because the heavier something is, the slower the object will move at a constant force. And if we exert a force on an object, the more force we exert, the more acceleration the object will experience. Bear in mind that in this condition, the mass is constant. Alright. But in this case, force should be constant. Alright. Now, what we have learned before is that now we can apply this to almost every single situation which we've learned before. We have learned the different situations of objects on a flat plane. We have learned about objects on a slope, and we have learned about objects on a vertical plane. Alright, so if we go into it further, if an object is in a flat plane, slope, and something hanging, on all occasions there would have to be a net force of some sort. In this occasion there'd be an applied force, which would then be counteracted by either a force of friction or completely frictionless. Same situation here. We can have an applied force, but we are always going to have the force of gravity, which would drag it down. Same thing with this object here. Alright, so the force of gravity would give us our force, our net force. Okay, now let's look at something like this example here. If this is 1 kilogram and we have an applied force of 10 newtons, and pretend that this is no friction. Friction is equal to 0. So it's going to be kinetic friction would be 0 newtons. So essentially what is going to happen with number 1 is that we only have a force that's applied in one direction, the force of gravity and the normal force. The force of gravity and the force of the normal force will cancel out, so the only force which actually gives us any acceleration is the applied force. So if we follow the equation of F net is equal to mass times acceleration, then the net force is 10 newtons. The mass is 1 kilogram, and A shall be A. So essentially, A is equal to 10 meters per second squared. But in terms of this diagram, right. Okay. Now, what you can see here is that if we have a force of friction, it would subtract from this net force. If we had a force of friction, it would reduce the net force. Okay, so if we take the force of kinetic friction to be 2 newtons, then we would have a counteracting force on that direction there. Now, our net force would then be taken in terms of 10 minus 2. Alright, if we were to put a step in before that, it would be the addition of the applied force plus the addition of the force of friction. But because, let's say, the direction of motion will be right, we'll take right as positive, so that's going to be positive, and we subtract anything acting in the opposite direction. So therefore, the net force is going to be 8 newtons right. Okay, now if we were to calculate acceleration, we would use the equation F net is equal to m times a and substitute it straight in. So therefore a is rather 8 meters per second squared, which would also be acting right. Okay, now in this occasion we can see how it changes is through the subtraction or the difference of the forces. Okay, now if we were to take this occasion, the next example, let's have a look at an example on a slope. Now, we're going to take theta as 25 degrees for an example, and we have an object where the mass is 2 kilograms in a frictionless example. Now, if we look at this example, this diagram, if there's no friction acting upwards, then the only thing acting on this object right now is the force of gravity. Now, because our direction of motion has to be parallel with the slope, then we have to break our force of gravity into its components. Okay, so we get the force of gravity perpendicular and the force of gravity parallel. And our theta will be that direction there. Now, this is the force which will be moving our object down slope. This force is just what will be acting into the slope. This makes sense because of the fact that if the resultant force is created from the resultant of 2 or more vectors acting in the same direction as one, then you can essentially go backwards and say that one force can be broken down into 2 different forces, and that's how we get those 2 things there. So we want to find force of gravity parallel, which is made up of the force of gravity and the sine component of 25 degrees. We don't know force of gravity yet, so we can calculate that. The force of gravity was made up of mass times the gravity, or acceleration due to gravity. Our mass is 2 kilograms. Our acceleration due to gravity is 9,8, which gives us a 19,6 newtons straight down. Right? Now we want to try and substitute that into the initial equation. We will get 19,6 sine of 25, which in the end gives us 8,28 newtons down slope. Now, that's not necessarily the end of our Newton's second law, because Newton's second law needs to find out acceleration. So if we're wanting to find acceleration is going to be equal to, well, let's go with the F net is equal to mass times acceleration. Mass is 2 kilograms, acceleration now we don't know, and the force is 8,28. So we get 8,28 divided by 2. So acceleration is 4,14 meters per second squared down slope. Okay. And if we go back to the final type, which you need to know, an object in the vertical plane. Either our object will be free falling, or it can be held up by a wire or a string. And the string will be light. It will be inextensible. Now, the reason why we call it light is so that there is no mass added to the system, and inextensible meaning that it will not stretch, which will then reduce the amount of force or impulse which is occurring in the body. Alright. Now, if it's attached to a string, there'll be a tension, but otherwise, there'll just be the force of gravity acting on it. If it's not moving, then the force of gravity is going to be equal to tension. If it's moving downwards, the force of gravity will be greater than tension. If it's moving upwards, tension is greater than force of gravity. That is around about it. So if we write that down,